The night sky has always inspired questions. One of the deepest is also the simplest. How does all this end? We now understand a great deal about how the cosmos came to be, but the universe's final act remains uncertain. To explore it, let's take a journey through space and time, from the final flickers of distant stars to the ultimate fate of matter itself. Think of it like reading a choose-your-own-adventure book written across the entire cosmos. Imagine you're strolling down a busy city street. Traffic flows, people chat, neon signs flicker. This is your world, full of energy and movement. Now picture that world in the far future, but empty, dark, and cold. No buzzing streetlights, no hum of engines, just silence. The end of everything is hard to picture, but cosmic physics gives us several possible endings: a slow freeze, a sudden rip, a fiery collapse, an endless cycle, and a quantum apocalypse. Each tells a different story about what might happen to space, time, and everything in between. First, the long, slow fade, the big freeze. It's the cosmic equivalent of a campfire burning down to embers. Right now, the universe is expanding, and that expansion is speeding up. Distances between galaxies grow larger, starlight stretches to longer, redder wavelengths. If that continues unchecked, the cosmic heat will disperse until there's no warmth left to share. In this future, stars will still shine, but not forever. New stars form by pulling in gas and dust. Over the next trillion years or so, that raw material will be used up. Long-lived red dwarf stars, tiny compared to our sun but frugal with their fuel, may burn for trillions of years. Eventually, even they will exhaust their hydrogen. The night sky will fade as the universe's last stars wink out. Only compact remnants, white dwarfs, neutron stars, and black holes will remain. Black holes dominate the next act. They swallow remnants and drift through the darkness. But even black holes aren't eternal. Over unimaginable spans of time, black holes slowly leak radiation, shrinking and cooling until they evaporate entirely. Energy becomes thinly spread. The cosmos cools toward absolute zero. With no gradients of temperature or pressure, nothing can happen. Energy still exists, but it's evenly diluted across space. This is the end, called the heat death. If you could stand on a planet in this future, assuming planets remain at all, you'd see an empty universe. Nearby remnants would provide faint warmth for a while, but beyond them lies endless blackness. Galaxies beyond your own would have receded so far and moved so fast that their light could never reach you. Eventually, even the cosmic microwave background, the fossil glow of the Big Bang, would redshift away until no instrument could detect it. What's left? Only a thin fog of photons and neutrinos slowly diffusing. It's a cold, quiet ending, but an ending all the same. Now the violent tear, the big rip. To understand it, consider why the universe's expansion is accelerating. Scientists attribute this to something called dark energy. We don't know what dark energy is, only that it behaves like a repulsive force on cosmic scales. If dark energy remains constant, the universe will likely drift toward a heat death. But what if dark energy isn't constant? What if its repulsive power grows over time? In that case, the expansion doesn't just continue, it speeds up faster and faster. Imagine stretching a rubber band. If you pull it gently, objects drawn on the band move apart but keep their shapes. Now imagine the rubber band expands so violently that everything drawn on it is torn apart. In the Big Rip scenario, the repulsive force inside space becomes so strong that it overcomes all other forces: gravity, electromagnetism, even the nuclear forces holding protons and neutrons together. Galaxies are ripped apart, and then star systems, then planets, then atoms. The fabric of space stretches until nothing can hold itself together. This process would proceed from large scales to small. Galaxies would break into individual stars and star clusters. Then the dark energy would pull stars away from planets and planets away from moons. The tear would then drill down to molecules, atoms, and subatomic particles. Eventually, space itself would be torn so violently that the equations we use to describe physics break down. The Big Rip ends the universe in a finite time, perhaps tens of billions of years after our present era. Fortunately for us, this outcome is speculative. It requires exotic forms of dark energy that conflict with other observations. Most cosmologists consider it unlikely, but it remains an intriguing reminder of how little we understand about the cause of cosmic acceleration. There's also the fiery reversal, the Big Crunch. Instead of expanding forever, the universe could stop expanding and begin collapsing. Gravity is the attractive force that pulls mass together. For decades, astronomers wondered whether there was enough matter in the universe to halt the expansion. If the density of matter were high enough, gravity would slow the expansion, then reverse it. Galaxies would fall toward one another. The universe's temperature would rise as everything compressed. Picture the cosmos as a giant balloon. In the Big Bang, that balloon expanded rapidly. In a big crunch, the balloon stops growing and starts shrinking. Distant galaxies that are now receding turn around and race toward us. Collisions would become more frequent. Galaxies would merge into superclusters and then into supergalaxies. Starlight would be compressed, shifting to higher energies. Radiation that is now gentle and redder would blue shift into ultraviolet and eventually gamma rays. Space would fill with intense radiation. Heat would rise everywhere. As the collapse continued, the universe would grow smaller, hotter, and denser. It would end in a fireball that looks at first glance much like the Big Bang in reverse, and some thinkers have proposed that the Big Crunch could bounce, triggering a new Big Bang. In this view, our universe might be one cycle, in an endless series of expansions and contractions. The appeal of this oscillating universe is that it sidesteps the question of how everything began. Each cycle resets the clock. Modern measurements, however, find that the universe's expansion is speeding up, not slowing down. That accelerated expansion makes it unlikely for gravity to reverse the cosmic flow. Still, if dark energy changes with time, if it weakens or turns into an attractive force, the universe could still turn around. A big crunch might be improbable, but it cannot be completely dismissed. Another vision is a cosmic heartbeat, the Big Bounce. What if the universe doesn't have one beginning and one end, but instead breathes in and out like a living organism? The Big Bounce is less of a single model and more of a family of ideas in which our universe is just one heartbeat in an eternal cycle. In bounce models, the universe undergoes repeated phases of expansion and contraction. A bounce might happen because quantum gravity effects kick in at high density and prevent a singularity. Or it might occur because our three-dimensional universe is embedded in a higher dimensional space where brain worlds collide and rebound. Imagine a slinky toy. Stretch it out and let it spring back. Each cycle stretches and compresses the coils, but the slinky as a whole endures. In some bounce scenarios, each cycle erases information from the previous one. In others, hints of past cycles might persist, imprinted as subtle patterns in cosmic background radiation or gravitational waves. So far, no evidence for cycles has been found. The data we have fit well with a universe that started from a hot, dense state 13.8 billion years ago and has been expanding ever since. Yet bounce ideas persist in theoretical physics because they address puzzles about the beginning of the universe, like why it was so uniform and why it had such low entropy. The Big Bounce invites us to imagine time as a circle rather than a line. If this were true, the end and the beginning would be relative terms. Each Big Crunch would segue into a new Big Bang. That means that what we call the future might one day become someone else's past. Finally, the quantum catastrophe, vacuum decay, or the Big Slur. To understand it, we need to talk about the Higgs field. Discovered in 2012, the Higgs boson is evidence of a field that fills all of space. Particles gain mass by interacting with this field. Quantum calculations suggest that the Higgs field's current value might not be the absolute lowest energy it could take. It may be what physicists call a false vacuum, stable for now, but not forever. Picture a ball sitting in a shallow depression on a hillside. It might sit there for ages, but it isn't in the deepest valley. A small jolt could cause the ball to roll into a deeper valley. In our universe, a random quantum fluctuation could make a tiny region of space tunnel into a true vacuum, a lower energy state with different physical laws. That region would form a bubble. Inside the bubble, the basic constants of nature, like the speed of light, the charge of the electron, and the strengths of forces would be different. Atoms wouldn't hold together. Chemistry wouldn't work. the bubble would expand at close to the speed of light. Anything it touched would be destroyed instantly. Because it travels so fast, the bubble would give no warning. You wouldn't see the end coming, it would simply hit you. On cosmic scales, the bubble might never reach us if it starts beyond a certain distance, but because quantum tunneling can occur anywhere, it could also begin right here. This might sound terrifying, but calculations suggest the vacuum of our universe is extremely stable. So stable that it would take far longer than the current age of the universe for a tunneling event to occur, even if it's possible at all. And if our understanding of quantum fields changes with new physics, the entire scenario might evaporate. Vacuum decay is fascinating because it ties together the largest and smallest scales. A process happening in a tiny region could doom galaxies across billions of light years. It also highlights how contingent our existence is. Our very atoms depend on the Higgs field being just so. It makes us appreciate the stability we have, at least for now. So which fate is most likely? Scientists gather clues. They measure the expansion rate of the universe, the Hubble constant, and observe whether it's speeding up or slowing down. They map the distribution of galaxies and galaxy clusters to determine the density of matter. They study the cosmic microwave background to learn about the early universe's geometry and composition. All these observations suggest that space is nearly flat and that the universe will keep expanding indefinitely. In this picture, a heat death becomes the most likely outcome. But science is about confronting uncertainty. Dark energy is still a mystery. The discovery of the Higgs boson opened the door to vacuum decay discussions, but particle physics may yet reveal stabilizing forces. New telescopes, such as the James Webb Space Telescope, Euclid, and other missions, will refine our measurements of dark energy. The Dark Energy Spectroscopic Instrument has already hinted that dark energy might evolve over time. If it turns out to wane, the universe could pivot toward a big crunch. If it grows stronger, perhaps a big rip becomes plausible again. And if new measurements of the Higgs field and other particles change, vacuum decay might move up or down on the list of worries. Meanwhile, theoretical physicists probe the edges of our understanding. Quantum gravity, string theory, and loop quantum cosmology all offer different visions of what happens at high energies and densities. Some predict bounces, others suggest inflationary cycles. Still others tie cosmic fate to a multiverse where every possibility happens somewhere. Learning about how the universe might end is both humbling and empowering. On one hand, it underscores how small we are compared to cosmic timescales and energies. Even the most dramatic scenarios we discuss, stars burning out, galaxies torn apart, take place over billions or trillions of years. On the other hand, it reminds us that we are part of this story. The physics that governs stars and galaxies also governs the atoms in our bodies. The same dark energy that pushes distant galaxies apart also pushes on the space between us. When we study cosmic fate, we're studying our fate. The end of the universe need not fill us with dread. Think of it as the final chapter in an epic saga billions of years long. We happen to live in a chapter where stars shine, galaxies sparkle, and life can ponder its own origins and destiny. The universe might one day grow cold and dark, or tear itself apart, or collapse and rebound, or change its very laws in an instant. But none of these are imminent. Our sun will shine for billions more years. Human creativity has time to flourish. We could even become agents of cosmic change. Perhaps far future civilizations will harness energy from dying stars, build gigantic structures to survive long winters of darkness, or devise ways to travel to other universes, if such things exist. Each end-of-universe scenario tells a story not just about physics, but about ourselves. The heat death suggests patience and endurance. The big rip warns of runaway power. The big crunch speaks to cycles of death and rebirth. The big bounce offers hope that endings are beginnings. Vacuum decay reveals how the tiniest quantum events can have cosmic consequences. Together they invite us to wonder, what does it mean to exist in a universe with a story arc? What does it mean to be conscious on a speck of dust under a sun that will one day blow away? As we close this exploration, remember that the universe's end is not settled science, but an open frontier. Every new measurement, every particle discovered, every cosmic event observed adds a piece to the puzzle. The heat death remains the leading candidate, but the Big Rip, Big Crunch, Big Bounce, and vacuum decay each have their champions and their challenges. It's possible that none of them captures the true final act. The cosmos has surprised us before. It may do so again. What's certain is that thinking about the universe's end changes how we see the universe's now. It sharpens our sense of time and scale. It highlights how precious the moment is. And it reminds us that in a universe filled with mystery, the most important story is the one we write together here and now.